All right, so in this video, we're going to learn about something called an asymptote of rational functions. So if you remember this week, we're learning all about rational functions, which just means functions that involve a ratio, which is division. So the function that we're going to look at today is 6 divided by x. It's the same one we looked at in class. So if you were in class yesterday, take a minute and pause the video and try to make sure you know how to fill in the table for this function. I'll start with the easy ones, but you should be able to do this whole data table for this function. So the easy ones, so this is just 6 divided by 1, 6 divided by 2, 6 divided by 3, 6 divided by 6. When I get into, let's talk about these two because this is what we were focusing on yesterday. So 6 divided by 1/4. Well, how many 1/4 are there in 6 wholes? There's a lot of them. There's 24, right? Because if I take all my 6 wholes and chop them all into fourths, I get 24 pieces. So similarly, if I chop them in half, I get 12 pieces. So when I use these small numbers, I get big answers. And then when I use big answers, right, 6 divided by 12, that's just going to get me 0.5, or 6 divided by 24 is 0.25. So how does all this look on the graph? These little points are hard to plot, but I want you to just estimate. 1/4, this one won't fit, but 1/2 goes all the way up to 12. 1 goes to 6. Let me make my dots a bit bigger. 12, 6, and then 2 goes to 3, 3 goes to 2, 6 goes to 1, and then 12 goes to 0.5. So that should give you a chance to kind of see the graph, visualize the graph, right? It goes up really high and then comes down and gets really small. Okay, so this graph has something called asymptotes, which we're going to learn about what that means and kind of how to understand them on the graph. So first we're going to talk about what happens when x gets really small. So when we use really small numbers for x, let's see. Oh, I can't. Okay, sorry. Okay, when we use really small numbers for x, what happens? So take a minute and pause the video, copy down this table, and find these divisions. So if I use 0.01, 0.001, these really tiny numbers, 1/100th, 1,000th, 1/10,000th, what's going to happen to my outputs? So pause the video and do those calculations and see if you notice what's happening. So this is like saying, how many times does 0.01 fit into 6? Well, it's going to fit in 600 times. 6 divided by 0.01. Another way of thinking about it is like, this is like 1 penny. So you could think of this as saying, how many pennies are in $6? Obviously, it's going to be a lot of money, right? A lot of pennies. And then how many tenths of a penny are in $6? So that's going to be 6,000, right? So each of these numbers is going to get way bigger because the tinier the number it is, I think that's 600,000. Okay, so what do we have? We have 6,000, 600, 6,000, 60,000. Okay, so what happens when x gets really small? What happens to the outputs for y? They get really big. They go shooting up. In fact, if you look on the graph, they just go shooting straight and straight up, which means they're getting closer to infinity. So the smaller number that I plug in here, the bigger number that I'm going to get out over here. So as x gets, the closer that x gets to 0, the bigger that y gets, right? It gets bigger and bigger. And this is like a key concept in math. This is called an approach statement. This is definitely a pre-calculus concept and a calculus concept. So write that down because we're going to be writing a lot of approach statements. So this little arrow is saying as x gets closer to 0, y gets just shooting up. Y shoots up to infinity. Why does this happen? So it happens because when I'm fitting these tiny little numbers into when I'm fitting these tiny little numbers into 6, they fit in many, many, many more times. Okay, now here's the key vocabulary. Where does the graph show this? This is called the vertical asymptote. And this is where the graph just shoots straight up to infinity. So the vertical asymptote is this line right here. It's the x, in this case, it's the y-axis. It's the line where x equals 0. So we're going to write that down and understand it better later. But the vertical asymptote of this graph is x equals to 0. We can't plug in 0 for x, but when we get really, really close to 0, our outputs get really, really big. So that's the vertical asymptote. This graph also has a horizontal asymptote. So we're going to talk about that now. So the horizontal asymptote is what happens when x gets really, really big. So just like we did last time, why don't you take a minute and plug in these numbers for x. So 6 divided by 10, 6 divided by 100, 6 divided by 1,000, and write down the little data table to show what happens to your outputs. So you're going to get decimals, right? This is going to be like, hopefully you tried this, 0.6, 0.06, right? You're getting these really tiny numbers. Sorry, my handwriting's not great. Okay. Okay. So when x gets really big, what happens to the outputs for y? They get really small. Right? They get tinier and tinier. So as x goes to infinity, meaning x is just getting bigger and bigger and bigger, y gets really close to 0. Right? These answers are super tiny. So the bigger and bigger that x gets, let me try to write this neatly. Sorry, my handwriting's so bad. The closer y gets to 0. Where does it show up on the graph? So this shows up on the graph by how this line right here flattens out almost to 0. And this is called the horizontal asymptote. And so this is the line of y equals to 0. So when x is getting really, really big, y is getting really, really close to 0. So the asymptotes are two lines that the graph will never touch, but gets closer and closer to. So let me write that down so we have kind of a definition of an asymptote. So an asymptote is a line that our graph never touches, so that our graph gets closer and closer to, but never touches. So we're going to try to investigate different asymptotes of different equations, but these are these lines that it kind of looks like our graph is almost like getting up right next to, but won't ever cross or touch. We're going to do one more example involving a vertical shift of this graph and seeing how that changes the horizontal asymptote. So let me start you guys off so you see how to create the data table for this function, and then I want you to pause it and try to fill out the rest. So let's do the easy one. We'll start with 1. So if I plug in 1, it's going to be 6 divided by 1. Let me make this a lot neater, sorry. Okay, if I plug in 1, 6 divided by 1 plus 5. So what's my output going to be? Well, 6 divided by 1 is 6 plus 5 gets me 11. So take a minute and pause and at least see if you can fill in the data table for those 4 entries. And then come back and I'll show you the rest. All right, so you should have tried it. 6 divided by 2 is 3. 3 plus 5 is 8. 6 divided by 3 is 2. 2 plus 5 is 7. 6 divided by 6 is 1. Plus 5 is 6. And then let's do the weird ones, so the tricky ones. 6 divided by 1/2, we know that's 12. Plus 5 is 17. 6 divided by 1/4 is 24. Plus 5 is 29. And then these will be 6/12 plus 5, so that's 0.5 plus 5. Okay. And then that's... So if that part doesn't make sense, make sure to ask about it in class tomorrow or pause the video and try to figure out where I got those numbers from. And then we're going to sketch a graph of this. So on my graph, I have the dotted line of the graph we just did. This graph is showing 6 divided by x. So how will this new graph this new data that we just found relate to this old graph, to the original graph? So 1/2 goes to 17. 1 goes to 11. 2 goes to 8, 3 goes to 7, 6 goes to 6, 12 goes to 5.5. So as you're looking at it, it should look like the exact same shape, but shifted up 5 units. So this plus 5 is a vertical shift up 5 units. My graph just moved up 5 spaces. So how does that change our asymptotes? So maybe you can kind of imagine or visualize before our asymptote was right here at 0. Now you can see by looking at these numbers, it looks like it's kind of getting closer and closer to this line right here. So we're going to talk about that by looking at some data. So when x gets really big, what's happening to our outputs for y? So take a minute and why don't you fill in this data table? Think about how it'll be related to the previous one. So if I use 10, well, 6 divided by 10 is 6/10 plus 5. So it will be 5.6. So pause the video for a sec and try to fill out those last 3 entries and see what you notice. Okay, so you should have noticed that I'm getting closer and closer. The little decimal part of my number is getting smaller and smaller, but the 5 is always staying because I'm adding 5 in. So in this case, when x is getting really big, what happens to the outputs for y? They get closer to 5, right? 5.006 is basically 5. So when x gets close to infinity, y gets close to 5. So the bigger and bigger that x gets, let's really work through this. So when x gets bigger, what happens? So the closer 6 divided by x gets to 0. So 6 divided by x plus 5 gets closer to 5. So where does the graph show? Where does it show up on the graph? It shows up by this little horizontal line right here that our graph is going to get closer and closer to, which is the horizontal asymptote. And in this case, my horizontal asymptote is y equals 5. So what's important to know is that my output's never going to equal 5. So 6 divided by x plus 5 will never equal 5. Why not? Let's pretend we're solving that equation. I'll subtract 5 from both sides. And so 6x would have to equal 0. But we know there's no number you can put in for x that will make this equal to 0. So that's not possible. So I can never get 5 as my output. But the bigger my x gets, the closer my answer gets to 5. And so that's why 5 is called the horizontal asymptote. So we'll practice it more in class. But the key concept, which we're going to learn about more, is that when you have an equation that's in... We're going to learn more and more about the form of rational function equations. But for now, we'll look at an equation in this form. So y equals something divided by x plus something. And this k causes there to be a vertical shift, which changes the horizontal asymptote. It's okay if that doesn't make total sense to you yet, but we're going to work on that more in class.